Alright, we're going to talk about why example 2 is going to work. And once again, we're going to do the same thing we did for the last problem. I'm going to rewrite the objective function with y by itself on one side. So I'm going to subtract the 100z, the 100x from z. So that would be 100x. So z minus 100x and then equals 300y. Then I'm going to divide everything on both sides by 300. Alright. So we get z divided by 300 minus, and I'm going to reduce this fraction, that's really the same thing as 1/3 times x, equals y. I'm going to write this as y equals the slope times the x, and then this is going to be our y-intercept. This time it's z divided by 300. Okay, so it's not the z value as the y-intercept, it's the z divided by z divided by 300 as our y-intercept. So I'm going to graph this once again in Desmos. So I'm taking my objective function, rewriting it as a line, y equals mx plus b. And I'm going to plug this into Desmos, and we're going to observe why this is working. So this is our feasible region that we just graphed. So the black line here is my objective function that we just rewrote. And here I have some values for z. So the z value is changing. We're making it increase, 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 decrease, decrease, decrease. Here's my constraints. So those are my inequalities. They're in red. So we said we wanted to look for a maximum and a minimum value, but we said if our feasible region, remember our feasible region is unbounded. So our feasible region is here, and then here, and then here. Remember it's to the right and above each of those lines. So when we're looking at this objective function, we said if z grows higher and higher and higher, well, it's never going to max out because we can keep raising it higher and higher and higher, and we're still not out of our feasible region. So the larger that z gets, well, we're still in our feasible region. We never actually obtain a maximum value because we'll never reach the top of that feasible region. So z never maxes out. So we weren't looking for a maximum, we were looking for a minimum. So we're looking for the smallest value that z can be. So right now we're not touching our feasible region, and so we're coming up, and the first value that we actually end up touching is a corner point right here at a z value of 700. Okay, so we can tell here that we hit that value when x equals 4 and y equals 1. So you kind of play around with making z as small as possible, but still touching that feasible region. So starting out really small, the first point that we touch on that feasible region with that line, z value of 700, that's the smallest that z can be, and it occurs when x equals 4 and y equals 1.